right, so when we get this set up, we do this derivative. You don't have to do this derivative by hand. You can do it on your calculator. So what Max had is fine, this version right here. But let's say it was no calculator, so we should be able to do this. So we could FOIL that out. We could combine these things together. We could come up with square root of this, which is 1/2. We get this. Now we should rearrange that a little bit. So the 10x minus 4 would be on top. This other stuff would be on the bottom. The 2 would be on the bottom. And then this would be the square root. This would be square root of 5x squared minus 4x plus 1. So let's talk about this as if it was a no calculator. Now what they did is they took a 2 out of the top and canceled with this 2, right? You see that? So on the calculator, they took a 2 out. The calculator did and canceled that 2. Now we're wanting to know when that's 0. Now, two important things here. We want to know when it's 0, but we also want to know when d prime is undefined. Well, when is d prime 0? Well, when the fraction is, 0. Fraction is 0 when the top is 0, right? Well, so that's easy. When is 10x minus 4 equals 0? Well, that'd be when 10x equals 4 and when x equals what? 2/5, right? 4/10, 2/5. So that's easy enough, even without a calculator. And then when is d prime undefined? When the bottom's 0, and even easier than that, the only time the bottom is 0 is when this inside the square root is 0. So we don't even need to do the whole bottom. It's just when will that be 0? So now we're asking ourselves, when will this be 0? Now, we do have a calculator, and so let's say we do have the calculator now. And so that would be something we could solve, because you can't ask, and Emily asked this yesterday, how do you tell if something's undefined? You can't tell the calculator solve when this is undefined, right? You can't do that. You can do a solve when something is 0 or something equals whatever, but you can't do when it's undefined. But now we know it's in the bottom is 0. So now just do solve and then do 5x squared, or 0 equals 5x squared, what was it, minus 4x plus 1. Let's see when that equals 0. And what's that mean? It doesn't equal 0, right? So we've now just answered the question that d prime is undefined, never. So we've now checked d prime undefined, it's never undefined. When is d prime 0? It's 2/5. Now, Max also could have went and just done this whole thing. Do a solve. Do a solve. Go up and grab your derivative up there. Grab that. Well, yeah, it'd be better to, grab the one up. That one. Grab that. I mean, you could just do that and then equals 0, comma x. If you weren't thinking, I mean, really, when is a fraction equal 0? Just when the top is 0. So you only have to really check when the top is 0. But you can do it, right? It'll still work out. Now, sometimes you do get some weird stuff with the bottom, but okay, so there it is, 2/5. So the calculator would take care of that for you too. Okay? So you get 2/5. So what have we forgot? What have we not done yet? Endpoints. What are the endpoints here? Endpoints, remember, are the x values. What's the littlest x could be? X could be up here, or here, or here, or here, or here. Negative infinity. There is no endpoints, right? But you need to discuss them somehow. So I would suggest this. I would suggest on your list of candidates, I would suggest that you do this. Okay, we have our distance equation. We're going to check d of 2/5. So I would suggest so this is a one candidate problem, isn't it? So I would suggest how many people did number line? Because that's what I had said, right? If you only have one candidate, if you don't have any endpoints, do a number line. So one option is to do d prime number line, put on 2/5. Okay, so pick something like 0 and 1. Plug that back into your derivative. Now Max has a derivative up here for us. So let's go grab that derivative again. Okay, grab that, do a vertical bar, x equals 0. We get a negative, and now do it again with x equals 1. And I think he's going to get a positive. So we got a negative and a positive, right? And so therefore, we've got this. And then we say, since d prime is always and I didn't see this on a lot of papers, so I'm just saying, this is, always negative before x equals 2/5, and always, the emphasis on the word always, positive after 2/5. D is always, so this is just like we were doing with local maximum, remember that? D is always decreasing before, and you can write this out a little better, but if it was a quiz anyway, I would. And always increasing after, so that is your minimum, right? Yes. Yeah, I don't think I said that yesterday, but you do. You got to make that connection between D and D. No, and so you wouldn't have to do this, right? Not if you're doing a number line, not if you have a single candidate. Remember, the only reason we're doing a list of candidates is so you can compare, right? Is so you can compare. Now, you could, but remember, in my notes, I said you have to make an argument for why it's a minimum. This would be an okay argument. For a single candidate, this would be an okay argument. Okay, this is saying that yes, this has to be the minimum, whatever. Now, you could also show a picture of the situation and say, you could treat your endpoints as this: negative infinity and infinity. Now, we're not going to say D of infinity. Infinity is not a number. But we could say this. You could do D of 2/5, right? And we could plug it into the D. And we could get that value, whatever that D is, whatever that distance is. Okay? And we could get that, whatever it is. And then here you could say, this is going to infinity and this is going to infinity. Because back here, when x is way, way out here, what is that distance? That is getting larger and larger. And when x goes to infinity, you're on points way down here, it's going to infinity. So you could write that in words too. So you could do a list of candidates and you could say as x goes farther to the left and farther to the right, the distance from the point 0, 1 is getting farther and farther and farther. So this has to be the minimum. Okay, you could do that too. That would be making an argument of why that is the minimum. So you could do a list of candidates when there are no endpoints. If the endpoints are literally infinity, you could make that argument. And you can do the same thing on a parabola, right? You could say, okay, this one candidate has to be the max because out here it's going down to negative infinity, so that has to be.
Doesn't that ask for that?
It may. Yeah, well, right. Remember, this is just step 6. This is just justify that it's a max or min or whatever. Then you have to answer the question. So I was just talking about the justification of that. You do have to answer the question. So, but they want the point. That's not the distance. Remember, this is the distance. This is 2/5 plugged back into the distance then. What you have to plug the 2/5 back into is this up here, right? So the final answer is going to be 2/5, and then you plug it in here. That'd be negative 4/5 plus 2, which is what, 6/5? What was the final answer? Is that what it? Isn't it? 6/5. So that's not the actual distance. So yeah, so you never do have to plug that 2/5 into the distance, depending on what you do. But you have to make that argument. Okay, next one. Some of these go a little faster. So this was that product one. We talked about 2 numbers add up to 10. You know it's going to be 5 and 5. The product's going to be 25, but the mechanics of it. Find what you're trying to maximize or minimize. We can solve this equation. We can subtract x, and so y is 10 minus x, so we substitute that right there. We get this. We do that. This would be so easy to do without any calculator. To do the derivative, which is that, set equals 0, we get 5. Our candidates would be the smallest x could be, I put 0. I don't know if it said positive numbers. Did it say positive numbers?
The example for
yeah. And it said 0 to 10. Okay. So I use 0 and 10. And so I put in 0, put in 10. Of course, when you do those products, you get 0 every time. So that's clearly your max. Put in 5. 5 times 5 is 25. MP prime, which is this right here, is never undefined. So there's your list of candidates. So that's a really easy one. right? That's a straightforward, nothing messy about it. Follow the steps kind of problem. Okay, let's look at 11. 11 is very much the same kind of problem. The thing that always throws people off on 11 is it just says, what is the minimum value of this expression? Well, you've got to call it something. Let's call it E for expression. I don't know, but you got to call it something. That's what always throws people off. They're always like, well, what is x cubed plus y? What do I do? Well, it's just like the last problem. So in other words, they've got this expression, x cubed plus y. They want you to find the minimum. Is it minimum? Minimum value. They want them to. So step one, what is it you're trying to minimize? This expression. Step two, write an equation for that thing. So we got E equals x cubed plus y. Okay. Step three, get it in terms of one variable. So you get y equals 4 minus x. So you're going to substitute that into there. So now we get E equals x cubed plus 4 minus x. Right. Then we're going to do E prime. And so we're going to do 3x squared minus 1. We're going to set that equal to 0. Go ahead and do that real quick, Max. It's 3x squared minus 1. Okay, so what were those root 3? Root 3. So I actually don't mind root 3 over 3. And negative root 3 over 3 is fine. Any endpoints? Did it give us any endpoints? It says x is greater than or equal to 0. So 0 to infinity is basically what we got. So that's fine. So what I think would look good on this, and I call it E prime. E prime is this. That's never undefined. So never. So we talk about that. Here's our candidate. So we're going to have E of root 3 over 3. We're going to have E of negative root 3 over 3. Oh yeah, because it's 0 to infinity, so we can ignore that. Yeah, good point. And then E of 0, so that does give us at least two candidates. We put 0 into this, we get 4. What'd you get when we put root 3 over 3? Just put root 3 over 3 into that. So
Which equation?
the original. Yeah, the original.
So it'd be the x.
X cubed plus, was it 4 minus x? Root 3 over 3 plugged into it. You can hit Control Enter to get a decimal. It's probably good because when you're doing list of candidates, it's always good to have decimals because then you get your so 3.615. So, and they want the minimum value. And then here's the other thing. So since your other endpoint is infinity, they just said x greater than or equals 0. I think it's a good idea to throw that in there. What's happening as x goes to infinity on E? It just gets bigger and bigger. You got x cubed, right? It just gets big. It's just going to infinity. So clearly, there is your minimum. And what did it say? What is the minimum value of the expression? Well, that's the minimum. Because E is 0 is 4, and then as x gets bigger and bigger, it just goes to infinity. So there's your minimum. So that's how you can show an endpoint of infinity like that. Okay, you can discuss it that way. But since we did have 0, it was okay to do just the list of candidates because we have two candidates there. But I think it's good to show that. Okay, we'll skip 17 for right now. Come back to it. So then the last one, this is just kind of your basic kind of rectangle kind of thing again. So you've got a perimeter. Farmer's going to fence this as inexpensively as possible. The fencing is $1 a foot. That makes it easy. Sometimes they'll do different costs for different sides of the fence, so you have to take that into account. You got $40 available in Part A, and so the perimeter. So they tell you a whole bunch of the stuff, but perimeter's that, the area's that. So we know we got 40 meters of fence, or $40, but it's $1 a foot. So $40 is the same as the perimeter, and so we get y equals that. And so now we just substitute that back in. So we get a equals x. And then 20 minus x. So this is beginning to look very much like those other problems we were doing. Again, we got an upside down parabola, so we know it's going to be a max, but again, let's just go through the steps. Oh, I did it over here, I guess. Never mind. So I got it over here, 20 minus x, do my a prime, it's a simple little derivative, I get x equals 10. Okay, of course the littlest x can be is 0, and the biggest x can be is 20, and that comes back to this right here. The littlest, they didn't tell you this, but the littlest x could be is 0, and then you would use all $40 for the y. If x is 0, you still got $40 to spend on fence, so you would use 20 here and 20 here. The biggest x could be is 20. If you use 20 here and 20 here, then that would be use up your 40. Okay, and so then the y would be 0. Often that's the case when you have two variables. The littlest one could be is when the other one is the biggest. And the biggest x could be is when the other one's the littlest. Okay, so that's how I got 0 and 20 as my two inputs. Okay, so but again, you're asking yourself for your input, what's the littlest x could be, what's the biggest x could be, that's your input. Okay, and so that's why I plugged those two in. Now this could have been one where you didn't consider the endpoints and you discussed something like, hey, A is a parabola upside down, it's got to be a max, right? You could go into that kind of discussion when you've got such a simplistic equation. You could do a number line and just say that 10 is your only candidate because it's always going to be increasing before 10 and it's always going to be decreasing after 10. So you could use that as a max, but I think it's simpler. It's just as simple just to consider those endpoints. It's good practice too if you get those endpoints. Okay, so you got several of them that work out pretty nice, pretty basic. The first one was a little harder to set up, and then of course there's 17. 17 is the world famous Shanghai problem. Can you imagine? So I'm assuming none of you are going to be going to the University of Shanghai, because this is on their entrance exam, it says, right? In 1999. Now it's probably harder. Okay? All right. Now, so the key to this is getting some things labeled and getting some things set up. And this is what I was looking for when I went around. And some of you did. I mean, some of you tried. We don't know what to do something. But, some of you, if you didn't even have the parabola drawn or a triangle, I mean, come on. You can do that at least, right? I mean, do something. When you don't know what to do something. But it's a really hard problem the first time. Now, you are going to hear me talk about this a lot. Now, actually, there's another problem we're going to do, and with Star Wars and everything kind of being in the news last year or whatever, we've got another problem later we're going to do that involves Luke Skywalker, and it's very much like this problem. So most of the year we call it the Luke Skywalker problem, but right now this is the Shanghai problem. And so what's going to happen, hopefully, as we go throughout the year, is we're going to run into these problems. And you're hopefully going to get to the point where you go, oh, I recognize this problem. This is a Shanghai problem. This is a Shanghai problem. And then I'm going to do it like we do the Shanghai problem. So we're going to talk about what the key to this problem is. So this is really hard. I didn't expect many of you, or hardly anybody, to get it. And as far as I know, nobody has. Now, I had a few people come in and were close. Joe Bennett came in this morning, and he was really close. But, most of the time people don't get much of this. So what I've done is 1 minus x squared, that's easy. That's an upside down parabola. There's 1 right there. Okay? And then if you read the problem, it talked about it was inscribed in this triangle, which means it just touches, right? I mean, you got to know what the word inscribed means. It just touches like so. Now, I've labeled this where this crosses as b comma 0. Now, you got to understand, that's only going to be measured from here, right? Now, a triangle is 1/2 base times height, but if we're doing this whole triangle here, if we're doing the whole red triangle, the way I've labeled it, what's the area actually? What would be the area of this triangle using the b and the h that I've labeled here? There wouldn't be a 1/2 in here, would there? Because this b is just from there to there, right? So this would be actually 2b times h, and then half of that. So it would just be b times h. So Step one, identify what you're trying to minimize. We're trying to do the minimum of that triangle area. So area of the triangle is what we're trying to minimize. Step two is write an equation for that area, which I've got. Step three is get it in terms of one variable. Wow, in this problem, step three is a doozy. Step three is the hard part of this problem. Getting this into one variable is what's hard about this problem. Okay? Now, I've got a picture of this scenario that maybe it'd be worth showing to you right now. Oops. But then again,
There's
say number 17.
it's Shanghai.
Shanghai picture. Yeah, that's the same picture thing. I don't know where that is now. Okay, anyway, I guess I'll have to look that up. Yeah, I know where it is. There it is. Right there. Okay, so this, I've just drawn half the triangle. So the idea is that, okay, you can look at your area. It's 5 1/4. So when the point's up here, the area is a lot bigger. When you come down here, the area, if you look at this area right here, that's getting smaller all the time. And so it's getting smaller, 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 and now it's getting bigger. So it's bigger, 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 smaller right through here, and then it's getting bigger, right? So we're trying to find that point right in there where that area is the smallest. Okay. Now, if I had the whole triangle, then both these sides would be moving at the same time. Okay, but that's the gist of this problem. Okay, so we're trying to find this point. We're trying to find that point of tangency that will give us the smallest triangle. That's what we're trying to find. Okay. All right, so we've got to somehow connect B and H somehow with one variable. Okay, is it going to be B? Is it going to be H? Well, it turns out the way I'm going to do it now, if you took a picture of the answer book, I'm not sure if you did, I know a bunch of people in our class were doing that. So when I walk around, I'm sure I'm going to see a lot of people just have written down whatever was in the answer book, which is a weird way to do it. I would not usually do it that way. But here's what you need, and here's the key to the Shanghai problem right here. 2 different ways to write slope. We have 2 different ways to write slope. You have your algebra 1 way. What's the algebra 1 way to write slope? Rise over run, 2 points, right? Subtract the y, subtract the x's, right? And we have the calculus way to do slope, which is what? The derivative. The derivative, right? So right here, remember, slope, the derivative is the slope of the tangent line. So this line right here, so let's ignore this side because it's basically the same. It's just going to be a mirror image. So this point, this line right here, we have 2 different ways we can do the slope of that line. One way is we could subtract the 2 points. So we can do h minus 0 over what? If I did these 2 points on the end, 0 minus b, right? So that's h over b negative, right? That's one way to write the slope. Another way to do the slope, though, is the derivative of the parabola, right? The derivative of the parabola is negative 2x. That's also the slope of that line, right? That's also the slope of that line. Now, not only that, but I've got another point in here that I can do my slope with. All 3 of these points are on this line. So I could do h minus y and 0 minus x. That would be the slope of that line. And I could do these 2 points down here. I could do y minus 0 and x minus b. That would be the slope of that line. All 4 of those things then are going to be the slope of that line. Okay, and they all have to be the same, right? They all have to be the same. So why not just set them equal to each other? So the key to the Shanghai problem is two different ways to write the slope and put them equal to each other. So what I would recommend is, I would recommend taking, well, it turns out we have two of them here that we could use. So I would recommend doing this one. Let me see, what would I recommend? No, I wouldn't recommend that. I would recommend taking these two right here. Because don't we have something we can substitute for the y? What can we put in place of the y? 1 minus x squared. So I know that negative 2x is equal to, oh, I actually have two of these I'm going to have to, I forgot I have two of these I'm going to have to do because I got b and I got h, but you'll see there. So I'm going to take these two and I'm going to set them equal to each other. So I'm going to have h minus y, so that's going to be h minus 1 minus x squared over negative x, right? Because of that right there. Now, I could be using my calculator right now, and I could solve this for h, okay? Or I can just do it myself, right? Let's just do it ourselves. Let's solve this for h. So I'm going to multiply the negative x over here, so that's 2x squared. And I get h minus 1 plus x squared. So let's add the 1 over there, and let's subtract the x squared over there. And don't I get h equals x squared plus 1? Isn't that what I would end up with there? Okay, and I'm going to hang on to that. And then, what about these two? What about putting these two together? Now, a lot of times, this is a little harder version of the Shanghai that we run into a lot of times. A lot of times, we know one of these points up here. We either know 0h or we know b0, so we don't have two different variables we're messing with here. But so I have to do this twice. So I'm going to take these two because I know what h is now. H is x squared plus 1, right? So I'm now going to take this guy. Let's change colors here. Let's do black. So now I'm going to take this guy. I'm going to take negative h over b, and that's got to equal negative 2x. But I know what h is now, right? Is this. So I'm going to change that negative h to negative x squared minus 1. Right, because it's negative, I got to make both those negative, over b equals negative 2x, right? With me so far? And now I'm going to solve this for b. So now I'm going to multiply the b over to that side, so I got negative x squared minus 1 equals negative 2xb, and then I'm going to divide by negative 2x. So I get negative x squared minus 1 over negative 2x. Now, I'm going to take out a negative top and bottom, so I'm going to get x squared plus 1 over 2x, so I don't have all those negatives. And isn't that equal to b right there? Okay, so there you go. So now that was all step 3. Step 3 was get it in terms of one variable. Well, that, like I said, is a doozy. Okay, so what we end up with, if I can go over to, I'll go over to my other page. So we end up with a is equal to, and then what was b? B was x squared plus 1 over 2x times, and then h was x squared plus 1. And I think I got that. I think I got that right. So again, if you look in the answer book, they eventually come down to that. They eventually get to that same point. And I could make this into x squared plus 1 squared over 2x. Right? So I eventually end up getting the thing I'm trying to minimize turned into that. But the key was we were trying to get this in terms of one variable. And so we had two different ways to write slope. So the more than anything, what I want you to remember out of this problem is what we call the Shanghai problem is we have a tangent line. Because up till now, whenever we've had a tangent line on a graph, we've always known what point we wanted it to be tangent at, right? We always said find the tangent line at x equals 1 or x equals 7. Well, here what we have is a tangent line at a point we don't know. That's the type of problems we're going to run into later on when we're going to go, aha, this is a Shanghai problem. It's tangent at some point x that we don't know. That's when we're going to say, hey, two different ways to do slope. One is a derivative of the graph, and the other is the 2 points, slope between 2 points. Okay? All right. So, now we just go the rest of the way from here, right? What's the next step? Do the derivative. A prime equals blah, 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 blah. Set it equal to 0. See if A prime is undefined, ever. What would be our endpoints? Look at your x's here, right? What's the biggest x could be? Or littlest x could be? Well, let's just stay on this side of the... Because if it goes over here, then that's just the other half of the picture, right? So let's just focus on this half of the picture. So the littlest x could be would be 0. And then what's the biggest x? No. It could keep going. Because you'd have it, if it kept going, you'd just have a tangent line that would be like, you know, it'd be infinity. It could keep going. So it'd be infinity, which we should. So it'd basically be infinity. And what's the triangle going to look like if x is up here, if the tangent line's up here? So what's your triangle going to look like? It's not going to be straight, right? It's going to, what are you going to get? You're going to get an infinite area. But look at this. What are you going to get when x gets really, really big? Remember the limit problems we did for Christmas? Since you have high powers on top, you have way higher powers on top. When x gets really, really big, this area fraction is going to get really, really big. So the area is going to be infinity. So here you're going to get infinity when x gets, when x is 0, it's going to be undefined, right? That's going to be one of your undefined situations. Well, that's where you're not. So you can finish the rest of it. And so I think what you're going to get when you do A prime equals 0, you're going to get one candidate, and basically it's going to be that same kind of thing. I mean, the areas, when x gets up here, your triangle gets really, really big this way, so the area is really huge. When it's down here, it's really, really steep up this way, so the area is really, really big. So clearly that one point you're going to find is going to be the minimum, and that can be your justification. Okay? So that's a Shanghai problem. So again, it's still following those steps. So, right, what are we trying to minimize? It's area. We need to write an equation for area. Step 3 was the killer. Step 3 was get it in terms of one variable. But think how easy this step 3 was. Get it in terms of one variable, right? Here, this. Oh, they gave us this, so we just substitute, boom. So sometimes step 3 is kind of easy. Sometimes setting up the equation, get in terms of one variable, sometimes kind of easy. And when that's pretty easy, the problem's pretty easy. Then you just follow your steps. Do the derivative, set equals 0, 0 is undefined, check endpoints, list candidates, give your justification, whatever. But sometimes it can be a killer, right? And that's what happened on the Shanghai. Okay, it was just tough to do. Now that's my version of it. What the book, if you followed what the book tried to do, the book labeled this point A. The book labeled this point A and 1 minus A squared, like that. Okay, this tangent point, and they wrote the equation of this line. Okay, and so what did they do? Well, that's y equals the slope, which the slope is that, the derivative, right? And they put an a in there, so that's negative 2a. And then x minus the x coordinate, which is a, plus the y coordinate, which is 1 minus a squared. Right? So they wrote that as their line. They wrote that as this red line right here. Then what they did is they said, okay, where does that cross the x-axis? So they set that equal to 0. And they solved that for x. Okay? They said, where does this cross the x-axis? And they solved that for x. Well, that's their b. So that's how they found b. And then they said, what's h? Well, h is when you plug a 0 in for x. So they plugged the 0 in for x. So if you plug a 0 in for x, you get 2a squared plus 1 minus a squared. You get a squared plus 1. So when they plug the 0 in for x, they got a squared plus 1. Well, that would be the h. Well, that's what we have. That's what we have for the h, x squared plus 1. Right? But they call it a squared plus 1. Right? And when they solved this equation for x, they got their B. Now, in my experience, most people are not going to want to mess with that tangent line and doing that. To me, it makes more sense to just do slope with those points. Just do the slope formula with those 2 points and solve it that way. That's just, for most people, that seems to make more sense. Okay, today, just staying on the same theme of max and mins, but this I call the business packet. The business packet. This book, our book, does not have a lot of business applications. If you're going to be a business major, you will potentially just take, now, if I were you, Ryan's a business major, and why do I have 2 of those? My son's a business major, and he just took regular Calc 1. Well, then he decided to double major with math, so he's taking other calculus. But if you're a business major, you could just take this business calc or applied calc, okay? But you can also take regular calc. Well, if you take applied calc, they do more of these kind of applications. So I wanted to throw some of these in because they're good. Because we talk about profit, doing max profit. They're good for max min problems. Okay, so some business terms you're going to need to know. So you might want to put these in your notes or circle them in the packet or something like that. Okay, but this is just some pages I've copied out of another book. If you turn to the page 216 in the packet, all right, so some business terms we want to do. X is often, not always, but it is often number of units, and that could be made or sold, and a lot of times they make those the same. In other words, if we're going to make so many units, we'll just assume we're also going to sell that many units and not have leftover. Now that's not always true. Sometimes you make too many and then you can't sell them all, whatever. Okay, so now it doesn't mean X is always a number of units, but often it is. Often it is. But there will be times in here where X might be stand for something else. Little p, lowercase p, is price per unit. Okay? Now, that is sometimes called the demand function. Little p. Because the price is based on demand. The price per unit is going to be a changing amount. Little p is usually going to be some sort of an expression with x's in it. Depending how many you make, the price may fluctuate. And if you look on page 216, if you look at that left-hand picture, right, with that kind of decreasing concave up graph, that first picture on page 216 there in that packet, it's going down and then kind of concave up. That's kind of a typical price function, demand function. As you make more of something, a lot of times the price tends to go down. If something's more hard to get. I remember there was a time, does anybody have a Wii? There was a time where those were really popular. You don't hear much about them now, do you? But there was a time where they were really expensive and you couldn't get them. I mean, they were sold out, and they didn't make very many. And that was kind of the strategy they had, I think. I think they could have sold a lot more of them. And their strategy was to kind of keep them in demand, and they could charge more for them. And I remember we talked about that as an example of doing this. Okay, capital R is your revenue, okay, which is usually X times P, okay? That's typically X times P. That is the money coming in. Right? That's the money coming in. So that's just if you sell 1,000 items and they're $2 a unit, then you've got $2,000 in revenue. Right? Just X times P. That's the money coming in. Okay? Cost. C is the cost function. Okay? That's the money going out, I guess you might say. Right? That's your labor, that's your rent on your building, that's your utilities, heat, electric, the paying your employees, the cost of materials to build the things. All of those things go into the cost. Okay, and then of course P, capital P, the big one that we're interested in is a profit. And the profit, of course, is revenue minus cost. That's a big equation you've got to know. Because, a typical problem is going to want to maximize the profit. We're going to want to do the max profit. So we're going to have to figure out our revenue, which we see here is our units times our price. That's our revenue, and then minus our cost. And that's going to be your profit. So in our steps for doing a maximum, step one, what are you trying to maximize? Well, a lot of times it's profit. If it's a minimum cost, you might be trying to minimize the cost, but maximum profit. Write an equation for that. Get it in terms of one variable. Usually that's pretty easy. Usually it's in terms of X. Usually it's in terms of number of units. So the cost problems usually aren't that tough. It's getting the price function. Typically the hardest part is getting the price function, right? Getting that, what P is in terms of X. And sometimes they're just going to give you that. Okay, now a couple more terms. C bar, C with a bar over top of it is average cost per unit, and that is just take the capital C function divided by X, right? That's the cost function, whatever that is, whatever your costs are, and then divided by X, the number of units, okay? And that gives you your C bar function. So we might want to minimize our average cost per unit. So we might want to minimize C bar. So you just take C and divide by X. Okay, and the last three then, P prime is called our marginal profit. So when you hear somebody talk about marginal profit, they're actually talking about the derivative. C prime is your marginal cost. And R prime is your marginal revenue. Right? And typically the lingo in business is when you maximize your profit, you're looking for a marginal profit of 0. Think about it. Think about it in calculus terms. Why would the marginal profit be 0? Slope is 0 at the peak, right? So to a business person, if they're in their lingo, if they're saying that their marginal profit is positive, what does that say? Their profit is increasing. But what does that tell a business person they should do? If their profit function looks like this, and they're right here, remember X is down here, this is P up here, X is the number of units you're producing. If you're right here on the profit function, what should you be doing? You should be making more. So if your P prime, if the marginal profit is positive, to a business person, that's saying we should be producing more. Because our rate of our profit is growing. Our profit is growing, so we want to keep going. If P prime is negative, well, if P prime is negative, it means you're making too many, right? Maybe by producing that much, you had to open a new building, or you had to pay overtime to your workers, or whatever, right? And so your costs are now out exceeding that, and your profits actually go down. You're still making money. P prime negative, you're still profitable, but you maybe aren't at your peak profit, right? So you might need to do some things to change that scenario, right? So that's how they talk. They wouldn't say prime and derivative and those kind of terms, but but that's what they're saying. They're looking for a marginal profit of 0. Tells them that they're at that they're kind of at that peak. Okay, so those are some of the terms that you're going to have. All right, so for tomorrow, so they talk about break-even point. Well, you know, if you start a business and you have to pay rent on a building and you have to buy materials and you have to pay, you start out in the hole, right? And so the break-even point would be where your profit equals your revenue equals your cost. Where your revenue equals your cost. Well, if your revenue equals your cost, what's R minus C? 0, right? If revenue and cost are equal and you subtract them, you get 0. Your profit is 0. That's your break-even point. When your costs exceed your revenue, of course, you're negative. You're in the hole. But your break-even point is when revenue equals cost, right? So those are just some terms that you need to know as you're going through this. Okay, so for your homework, so I think it says on the thing here, it says 4.3 day 2. So there's some problems in the book. I'm going to help you get started with those, with one of those, and then the business packet. You're doing number 3 and number 8, and it says that. Okay. All right. So I'm going to help you get started with number 28 on your homework. I thought I had a picture of that somewhere, but I guess I don't. So I guess we'll do that together. Okay. So go ahead and open up your book to that page, and let's take a look at number 28 and get started on it, because it actually has 2 parts. The third part we probably won't mess with. It has 2 parts, and each of the 2 parts have 2 parts. So let me see. Well, now we're going to skip part A and D. So we're just going to do parts B and C on 28. So I'm going to help you get started on part B. And then part C is very similar. Okay, so read 28B. All right, you got it?
Is that what FedEx stands for? Federalist?
No. FedEx is Federal Express. I think they just changed it maybe so that to avoid copy or not get in trouble for using Federal Express without their permission or something. But Federal Express, but they do charge you based. And they're always changing, but they do charge based on sizes and so forth. And so what they're saying is that they have a formula to determine what is considered a mailable parcel. Okay, it says the long side plus the girth can't exceed 108 inches. Okay, and that we want to find what's the volume of a rectangular prism or whatever, a box. It's a box, right? That's what they're talking about. They're talking about a box. Okay, a box-shaped thing. What's the largest volume that we could ship? So we'll assume that the largest would be the one that uses up all 108 inches, right? Now, but here's why there's 2 cases. They say there's 2 cases to this. Because one, so Emily, you're talking about picturing it. Well, you just got to be able to picture a box, Okay, so you're right, you got to be able to draw three-dimensionally. Now, you know, I know most people aren't going to be as great as drawers as I am, but it's got a square base, right? So one would be a tall, skinny box. So let's draw a tall, skinny box. I used to have some boxes around, but now we moved. So. Okay, that would be one example. Now, what can I label these? What should I label this down here? S. It's a square, so why not? S and S, right? What do you want to label this up here? I know you are, but I know L, that's not my favorite letter to use in a math problem. How about H? You can use L, right? I don't care, but L just is weird to use in a math problem. Okay? So step one, identify what you're trying to maximize. We're trying to do a max volume of a box. Okay? Step two, write an equation for it. So it'd be V equals S squared times H. Right? Step three, get it in terms of one variable. Well, this is where that 108 is going to come in. Okay? The long side, so what's the long side? The long side would be H. Now, what would be a box where the long side wouldn't be H? A small flat box, right? So that's going to be our second case. So if you want to go down the page a little farther and draw yourself that situation would be where we have ourselves a box like this. And now H is not the long side. What's our long side? The volume is still S squared H, but what's the long side? The long side is now S, right? That's why there's two cases here. There's going to be two situations. So we're going to have to work out both, and then whichever max is the bigger max, that's the one we want to use, right? So let's go back to this one. So the long side is H. What's the girth? What they say the girth was?
Isn't this diagonal?
No, read it. What's it say?
One side plus, I remember the constant sheet.
Perpendicular to the longest side. So if this is the longest side, it's the perimeter around perpendicular to the long side. So wouldn't that be that perimeter right there? Perpendicular to the long side. So the girth of this would be 4S. So what did they say then about the long side plus, what was the 108? So H plus 4S can't exceed 108. So we could say less than or equal to, but I think we'll just assume if we're looking for the biggest box we can do, we're going to want to use up all 108 inches. Make sense? So we're going to want to use up all 108 inches. So there you go. Now aren't we just like the easy problems we've done? Isn't that now like an easy one like this? Where or even like this, where we now have an equation we're trying to maximize. We have a second equation we can now substitute. We do our derivative. We set equals 0. We do list mechanics. Blah blah blah. Right? Now we're there. Right? Now we're there. Because what are we going to do? So H is equal. I would solve for H, and I don't have to divide by 4. That'd be better. So let's solve for H. That'd be 108 minus 4s. Let's put that over there. So I get v equals s squared times 108 minus 4s. I can distribute that. I get 108s squared minus 4s cubed, right? I'm going to do my v prime, right? And I'm going to have listed. What's my endpoints? Because s is my input, so what's the littlest s can be? It's okay to put 0. You're right. Remember the box problem we did the other day? Obviously your volume is going to be what? 0. But that's okay. So the littlest s can be a 0. What's the biggest s could be? Well, again, that's if you used all 108 for s, right? The biggest s could be is if h was 0. So right here, if h is 0, what would s be? (108) divided by 4? (108) divided by 2 would be 54. Divided by 2 again, it would be 27. So your endpoints would be 0 and 27. Okay, now you can go from there, right? We can do v prime, we can set equal to 0, right? You can get the rest of that. Okay, let's go back to this side real quick. Okay, this other picture. What's the girth on this one? Wouldn't it be here, 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 and here? Wouldn't it be there? Isn't that perpendicular? Now, it could have went this way too, right? S is alongside, so it's got to be perpendicular to the long side. So how much is that? 2s plus 2h would be your girth. So the long side plus the girth, right? So it's the long side plus the girth has to equal 108. So that's going to be 3s plus 2h equals 108. So it's different, right? It's different. So now you got to solve for one of those. I'd probably solve for the h again, same thing, but whatever, right? And then you're going to have substitute, but you have a different scenario there. Okay, now, and right, that's only half of 28. Okay, you got a little work to do. But it's good practice going through the process. Now, 28C does the same thing except with cylinders. So you have a tall cylinder or you have a really short, fat cylinder, right? And what's the volume of a cylinder? Pi r squared times h, right? So you're going to have h here and you're going to have r here. So either h is going to be the long side or the diameter 2r will be the long side, right? You'll do your girth from there. So that's 28C, and it has those two parts.
Wait, what would your girth be?
Well, the girth would be perpendicular along side. Here's a long side, so in this one it would be this perimeter, which would be circumference, right? And on this one it'd be perpendicular here. So it'd be across here. That'd be your diameter. That'd be 2r plus h, 2r plus h. That'd be your girth there. Perpendicular to the long side. So if your long side's across here, that would be perpendicular. So the girth here would be 2r and 2r. That'd be 4r plus h plus h. Yeah, that'd be the girth on that one. And this one, the girth would be just the circumference. What's the circumference? No, that's area. 2 pi r. Circumference is 2 pi r. So that's your girth. Now don't forget, it's the long side plus the girth that equals 108 though, right? It's the long side plus the girth that equals 108. All right, go ahead and keep working.